Hello everyone, this is Anshu Narang. I'm part of NSO BU. I'll be covering NSO performance and scale test for reference use cases, NFVO and T-SDN. Let's get started. Okay, so we'll be looking into NSO scale and performance capabilities for two use cases essentially. The first one being virtualization or RFM-based use case, wherein essentially service reacts to different events from the device, or rather redeploys as and when it receives different events from the device. And that's NFVO core function pack. The next case we'll be looking into is physical device configuration use case, wherein we have a lot of devices or a lot of ASR 9K devices, wherein we're pushing huge set of configuration. And that's T-SDN core function pack. The intention here is to cover broader NSO usage. That's why we picked two use cases that are indeed different. And the information that I'll be sharing should help NSO users understand what to expect from NSO in terms of scale and performance. It will help understand the resource requirements for large-scale applications and, of course, with different deployment scenarios. And we'll be looking into different deployment options, and we'll also get a sense of where and how these deployment options can help achieve different use cases that you may have. Let's jumpstart with NFVO core function pack. Again, it's NFV orchestration space. So NFVO core function pack is Cisco's version of Etsy Nano NFV component. And function pack at a high level has two main responsibilities. One is to instantiate and manage lifecycle of the VNF on Vim, which can be OpenStack, AWS, VMware. And this is done through VNFM, which can be Cisco ESC, Elastic Services Controller, or any third-party Sol3 VNFM. And the second responsibility from NFVO is allocation of resources that are utilized by VNF upon instantiation. So our test focus is going to be on instantiation and management, lifecycle management, essentially. Before we get down to test, it's important to understand the NFVO service and the flow so that we understand what does it look like under the hood. And here you can imagine this NFVO installed on top of NSO. And there's a northbound integrated into NSO using any of the standard interfaces, and it kickstarts creation of the VNF. When it receives the creation of VNF, all interactions of NFVO southbound with the VNFM are adhering to HC Sol3 protocol here. And that's going to be focus of our test too. So NFVO would kickstart creation of VNF resource on VNFM. VNFM would respond back with the resource ID, and NFVO service would redeploy and kickstart instantiation of the VNF on the VNFM. So VNFM, upon receipt of instantiation request, would acknowledge it with starting notification. Followed by that, it will issue a grant request to understand where to deploy this VNF or which PIM to deploy it on. When NFVO responds back with the placement decision, VNFM would essentially kickstart creation of the VNF on the desired Vim. And behind the scenes, Vim would start working to actually bring the VNF up on the desired host. In parallel, VNFM would kickstart the keep alive check or check alive. Essentially, what it's trying to do is it's trying to see when actually the VNF has booted and can be pinged. There can be other possible checks as well. Once it identifies that the VNF is actually up and running on the host, it will send in a complete event to NFVO. And once NFVO receives it, it will essentially redeploy the service and essentially mark the plan as ready reached. Upon which case, we can assume the service has converged, which is it got to a ready state, it's up and functional on the network. You can imagine that there can be different variations and scenarios that are possible. And what we have tried to capture here is some of the commonly used options for NFVO. And they essentially span from number of services to number of VMs that a particular VNF may have, to number of VNFs that you intend to instantiate in one commit, and southbound integration options like Sol3, or managed VNF option, wherein you're allowed to manage this particular VNF or push configuration on the VNF that just came to life. And there are also a few deployment options that are listed, like LSA and HA. Along with that, you have an option of using commit queue as well. Again, these are most commonly used options. So let's jump to the next step, wherein we can see how this is leveraged. And for the test, essentially, we'll be covering the first two test cases. There are more, as you can tell from the picture, and those are being worked upon. Okay. Infrastructure and methodology. You can see the NFVO core function pack that's installed on NSO. Southbound, it's talking to Sol3 VNFM device. And towards its north, it's automation framework. And that's something essentially we built to be able to exercise different scenarios that we saw in the previous slide. And the other thing where it helps is it helps collect all the statistics from the NSO. And along with that, it gathers all the resource utilization information to understand how NSO behaves under different situations. And again, the intention here is to leverage it across the board, across all core function packs. Infrastructure, again, latest released NFVO along with the corresponding NSO, standard system configurations for scale. Jumping to methodology, as we saw in the previous slide, we'll be creating 10K services. Intention is to commit single service in the commit. And in order to facilitate, or in order to have multiple services being worked on in parallel, what we'll do is when we commit the first service from the automation framework, moment that commit returns, we'll kickstart instantiation of the next VNF. And that would essentially force NSO to have multiple services being worked upon in parallel. And idea is to able to understand how NSO works on these services in parallel. And as you can tell, creation of 10K services would really require a lot of physical resources to exist. So to keep resource requirements to minimal and to be able to effectively test NSO, what we leverage here is NetSims. And it essentially keeps all the external dependencies to minimal, plus it helps with minimal resource usage, to be precise. And again, it does allow for a few configurations to behave, to force more real-life behavior, like configuring time, wherein from instantiation to the complete notification, how long it takes. And we have by design configured that as 5 minutes to have more real life effect. Okay, jumping to the first test results. Again, these are for 10K service creates. Total number of VNFs is 10K. Single VM VNF, single VNF in transaction, as I mentioned, leveraging Sol3. And we will not manage the VNF in this case or for this test. Deployment option is simple, standalone NSO without commit queues. Let's jump to time-based statistics. Again, you can see, let me define the time to converge first. So essentially, if you imagine or if you remember the flow that I had shared, from the point when northbound commits the service to the point when actually VNFM sends the last event complete, followed by that service gets redeployed and marks plan ready. That is typically convergence of single service. And here what we're talking is the amount of time it takes for 10K services to converge. And that's really good, 14 hours and 36 minutes, close to 900 minutes. And keeping this data in mind, the average time it takes per service is about 11 services per minute. And that's really a good indication of parallelism that NSO can bring in. Average commit time is representation of response time that northbound would see. So imagine northbound committing the service. This is the average time that commit would actually take to return. And that's really well within control under high load. And it's fairly consistent as well from the data that we have seen. Jumping to resource utilization, memory, essentially, as we know, NSO stores all the configuration data in the CDB, and that is stored in the RAM, and that allows for quick access to the data as and when needed. So we do expect memory to increase with number of services, and here that's perfect. Disk, CDB, they all vary linearly. You would see slightly more disk utilization, and that's to cater to different events that we receive from the NFM. It's to help debugging and troubleshooting as and when it's needed. Again, this is next round of test. Again, configuration-wise, it's pretty much same as the first test. What's different here is we're executing certain tests once we are at certain scales. So imagine a system that has about 10K services existing on it. And on top of that, we're trying to create 100, 500, and 1,000 services. Aim is to see how NSO behaves with operations once they're done at certain scale. So as you can tell from the picture, this variation is linear. Like services to time is linear, and that's really good data and representation, or something that you would like to see. Along with that, services per minute is pretty much in line with the numbers that we saw with 10K creates, and that's also a good sign of healthy performance system. Let's jump to our next use case, and that's transport SDN core function pack. Again, this is around PNF orchestration. So transport SDN automation solution. Again, function pack has at a high level two responsibilities, L2 and L3 VPN configurations, plus it allows for segment routing policy configuration, which is going to be focus of our test, because these policy configurations are the ones that are pushed in bulk. Okay, like how we saw for NFVO, let's jump to T-SDN service flow. Again, you can imagine northbound integrating into NSO, pushing a create service or SR policy with list of devices. T-SDN service would essentially read this information, understand what devices need to be configured, what net to be used, and then they'll kickstart applying the device configuration on all the desired devices. Here we have two options, commit queue or non-commit queue. Let me explain a little bit on commit queue before we dive into the flow. So for T-SDN use case, especially, as I mentioned, there can be hundreds of devices that we need to configure. And with hundreds of devices, there's likelihood of one or multiple devices failing, or there's likelihood of network latency that you might see towards the device, or you might see network choppy at times. So commit queue definitely helps application scale and perform, especially perform for such cases. So as you can imagine, once the configuration is applied to the device tree, NSO would do the heavy lifting of pushing this configuration to the actual devices. And once that is done, it will redeploy the service and mark, and wherein the service would mark the plan as ready. If you look at traditional non-commit queue use case, the policy push is going to be part of the bigger commit, whereas in commit queue, the commit returns sooner, and you can start more things in parallel, and that's how it helps. Like how we saw for NFVO, there are different scenarios that we picked up. Again, most commonly used options is what we kickstarted with. So you can see number of services, services per transaction, number of devices used, and devices per service. And again, like how we saw for NFVO, there are different deployment options. And here we'll be leveraging commit queue. So let's jump to the infrastructure and methodology now. Again, T-SDN core function pack, southbound, it's talking to ASR 9K. This is the automation framework that I described. Again, it helps exercise all the scenarios that we saw, help collect resource information. That's imperative for the results. Infrastructure, we're using latest release T-SDN with the corresponding NSO. System configuration that's optimal for scale. And when it comes to methodology, we'll be creating 10K services similar to NFVO. We will not wait for services to converge. We'll continue to commit services moment the first commit returns, or previous service commit returns. The difference here is we are talking to multiple devices. So each service would be configuring about 4 devices, and we'll be picking up 4 devices from the set of 300 devices that we have in round-robin fashion. As for NFVO, we'll be leveraging NetSim here. The idea is to keep external dependencies minimal. Okay, jumping to 10K service create results. Again, single service in transaction, 4 services per device, and standalone NSO. We will be using commit queue here. Let's jump to time-based statistics. We can see the total time to converge is about 18 hours, 39 minutes, or close to 1100 minutes. And again, here, what convergence means is from the point when northbound committed the service to the point when NSO behind the scenes applied or pushed configuration to ASR 9K, followed by that service redeploys and is marked ready. And that too for all 10K services. That's about 18 hours and 39 minutes. And again, it's a little bit higher than NFVO, but it's still pretty good and expected given we're using commit queue. We're configuring more devices, higher amount of configuration as well. Average time per service, looking at these numbers, would be about 9 services per minute. And that's again, excellent example of parallelization that NSO can help achieve. Average commit time is indication of response time that northbound would see. And here it's a little bit higher than NFVO, and that's because of the amount of configuration that we're pushing to the devices. And of course, the number of devices in question as well, and which is more compared to NFVO. Memory utilization is as expected is more. NSO is storing more in the RAM, and that is expected to increase. But the growth is linear. So that's what you expect from a healthy performance system. Disk and CDB usage, again, has to be higher. And here, the amount of logging needed is less. That's why most of the disk usage is coming from the CDB growth, as you can tell from the data. Next test result, like same as NFVO. Once we have 10K existing services, our aim is to create 100, 500, and 1,000 services on top of 10K, and then see how NSO behaves. Use case wise, it's exactly same as the previous test that we saw. We'll be using the exact same deployment options, number of devices, and services per commit. So as you can tell from the picture, variation between service and time taken is linear, and that's really excellent. And so is services per minute. That's pretty much in line with the information that we saw for 10K create, 9 services per minute to be precise. And that's really excellent. Recommendations in summary, again, the scale and performance results that I just shared is to provide guidance around what to expect from NSO when it comes to scale and performance for your use case. And we should keep in mind that these results would vary with the use case and environment that we have. And we do expect users of NSO to try out scale and performance tests against their use case at hand to get precise numbers or to understand the precise numbers. Another point worth noting here is when we're talking bulk operations, that is thousands of creates, deletes, updates, you need to just plan ahead, or these have to be well planned. And essentially, it's always good to avoid mixing certain operations. We should isolate bulk creations from other operations that we intend to do. Okay. Quick summary of what we saw. We saw NSO scales and performs pretty well for virtualization as well as physical device configuration use cases. From northbound integration perspective, you should see consistent response times under high load. And as we saw, we created thousands of services within a day. And we could see that about 10 services got converged in per minute. So there's real good parallelization happening. And when it comes to resource utilization, we could see it was optimal and growing as the number of services grew, which is expected. With that said, I guess if you guys have questions or need more details around the test that would execute it, feel free to reach out to us through usual channels. Happy to help. I hope you liked my presentation. Thank you.